Welcome back to elementary statistics. In this video, we're going to be going through some counting rules. We saw previously that in order to calculate a probability, the procedure is going to be calculate the number of outcomes in the sample space, calculate the number of outcomes in the event we care about, and divide those things. For simple experiments, rolling one die, drawing one card from a deck, counting up the number of possibilities is relatively straightforward. But we very often will want things that are more complicated. We will want to look at rolling, instead of just one die, two or three or four dice. Instead of drawing one card off the deck, we'll want to draw two or three or four. And when we're drawing cards off a deck, it might be that we are looking at dealing them out in a particular order, or it might be that we're dealing them out into a hand where we can shuffle them around without too much issue. And so we need some tools to count more complicated things. And that's what we want to look at today. I'll start off with a rule known as the counting principle. The counting principle tells us that for an experiment with multiple independent steps, the total number of possible outcomes for the experiment is the product of the number of outcomes in each step. The idea here of independent steps is one that we're going to investigate a lot more as we go onward. But for now, I want to look at a very simple example. That example is rolling two six-sided dice. When you roll a single six-sided die, there are six possible outcomes. If you've ever played a board game where you can roll two six-sided dice and add the results of the two dice together in order to make some conclusion about what's going to happen, generally speaking, the two dice are virtually indistinguishable. In order for probability to work, we have to kind of ignore that. We have to assume that there is always a distinguishing feature and we can tell which die is which. In practical applications, I'm often going to talk about this by rolling, say, a white die and rolling a red die. That way it's very clear which one is which. So in my experiment of rolling two six-sided dice, I roll a white die, which has six possible outcomes. In my experiment of rolling the two six-sided dice, I next roll a red die, which has six possible outcomes. According to the counting principle, that tells us that the number of possible outcomes in the sample space is 6 times 6, which is 36. Right? And you can think about that, you can list them out. Right? In each of these outcomes, interpret the first number as the result on the white die and the second number as the result on the red die. We can have them both come out as 1. We can have the white die come out as 1 and the red die come out as 2. Or we could have the red die come out as 2, or trying to say the same thing twice. We can have them both come out as 1. We can have the white die come out as 1 and the red die as 2. We could have the white die as 2 and the red die as 1, and those are two different outcomes. We could have 1 and 3, we could have 3 and 1. We could have them both come out 2. We could have 1 and 4, we could have 4 and 1. We could have 2 and 3, we could have 3 and 2. Those are different outcomes. As another example, just to show you that we don't have to always have the same number of sides. If I roll an 8-sided die and a 20-sided die, there are 8 different things that can happen when I roll an 8-sided die. There are 20 different things that can happen when I roll a 20-sided die. And if I multiply 8 times 20, I get that there are 160 different possible outcomes for this experiment. And we can also extend outward. We don't have to restrict ourselves to just 2 steps. The same process works if we have 3 or 4 or 5 or 12 or 150 different steps in the experiment. For example, the experiment of flipping 5 fair coins. Well, flipping a coin has 2 possible outcomes, heads and tails. So the first coin has 2 possible outcomes, the second coin has 2 possible outcomes, the third coin has 2 possible outcomes, the fourth coin has 2 possible outcomes, and the fifth coin also has 2 possible outcomes. We could simplify that a little bit. Multiplying the same thing times itself multiple times, the shorthand for that is the exponent. We could write this as 2 to the 5th. You don't have to do that, but it tends to make things a little bit easier as far as putting the expression into your calculator. Right? If I told you I wanted you to flip 20 fair coins, counting out and making sure you punch it into your calculator correctly could cause problems. Punching in 2 to the 20th is a little bit easier. Right? But either way, in this particular case, we get 32. Right? But if I do extend that out and think about flipping 20 fair coins, well then n of s, the number of outcomes in this sample space, is 2 raised to the 20th power. And for this one, I definitely need my calculator, which of course shows up right where the problem is written, but that's okay. I can punch in 2 raised to the 20 power. My calculator is happy to tell me it's this lovely, easy to remember number, 1,048,576. Right, and there we have it. One more example on the counting principle, just to show that you can use this in things that really don't feel like experiments, but when you stop and you take a step back, you can convince yourself they are. Mathematics is wonderful at this sort of an abstraction. A car's license plate consists of a sequence of 3 letters followed by a sequence of 4 numerals. The state of Pennsylvania started issuing license plates using this scheme about 20 years ago or so. How many different license plates can be made following this scheme? Well, think about each step. We need to put a first letter down. We need to put a second letter down. We need to put a third letter down. Then the first number, the second number, the third number, and the fourth number. The letter can be any of the 26 letters in the English alphabet. So there's 26 different possible options for this letter. There's 26 different possible options for this letter and for this letter. The numeral can be anything 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. That's 10 possibilities for this number, and this one, and this one, and that one. And so we can rely on the counting principle. I can pull my calculator up one more time, which only partially covers the problem this time. But I can punch in 26 times 26 times 26. I could have shorthanded that with an exponent. Then we have 10, another 10, another 10, and one more 10, And all told, we get this result. 1, 7, 5, 7, 6, and then we've got 1, 2, 3, 4 zeros at the end. Working backwards and putting in commas so that we can see how to read this number. There are 175,760,000 different possible license plates that can be issued in the state of Pennsylvania before they have to change the scheme that they use to produce them. All right, moving along, I want to next look at a situation where the events are no longer, the sequence is no longer independent. When we're rolling multiple dice, the outcome of one die does not affect the other one. If you flip a coin and then you grab another coin and flip it, the first coin is out of the way. It's not going to change what happens with the second coin. Consider as a different example, taking a standard deck of playing cards, which unfortunately I don't have one in front of me. But take a deck of playing cards, shuffle it, deal one card. There's 52 possibilities for that first card. Set that card aside, hand it to a player, and then deal the next card. Because that first card is gone, the rest of the deck only had 51 cards. The third card you deal out, there's only 50 possibilities, and it keeps decreasing as you go. And so we need something a little bit more complicated for dealing with that. There are two functions. If you're really interested, the mathematics behind these aren't that difficult to get to, but I don't think it's worth the time. Right. The two tools are the permutation or pick function, which is written as NPR, and the combination or choose function, which is written as NCR. I'm going to need my calculator, so let's make sure I have enough space on the screen here. All right, I'm not going to go to the entire deck of playing cards because the numbers get pretty big pretty quickly, but let's look at something a little bit more manageable. Let's take a look at a situation where you have 10 people in a group and you need to select 3 of them for some task. Depending on the task, the nature of that selection can change. If you need 3 people to get up on the stage and mime out a scene, well, it doesn't really matter which one is going to do which. If you need 3 people instead to act out a part of a play where each person is going to have their own character, at that point, who gets which part changes what things look like. So when everything you select gets the same behavior, we say that the order does not matter. That's the combination or choose function. When everything that you select gets a different result, that's where we say order does matter, and that's the permutation or pick function. Right. So if I have my group of 10 people and I want to pick 3 of them, it would be 10 pick 3 if the order does matter, and it would be 10 choose 3 if the order does not matter. Almost all scientific and graphing calculators have these functions built in. Where you'll find it will vary from calculator to calculator. On my calculator, let's get that a little bit more in focus. That's a little bit better. On my calculator, I have a menu right here called PRB. If you have a scientific, or I'm sorry, if you have a graphing calculator, like a TI-83 or a TI-84, you probably have a button somewhere in that general vicinity that's labeled as math. And if you look in that, you'll find a menu below that that says PRB for probability. And the first entry in this is the NPR. I can use the arrow keys to scroll over and get the NCR. This last one is the factorial, which we're not going to worry about in this course. And then we've got Rand and Randy for generating random numbers, but those don't matter all that much. All right, so if I take 10 and I go into this menu, get my pick function, hit 3, hit enter, my calculator tells me the result here is 720. Right. If you don't have a probability menu on your calculator, take a look at the alternate text on keys. For example, right above the reciprocal key on my calculator, it says EE for scientific notation exponent. Oftentimes on calculators, you'll find the NPR and the NCR features hiding in that way. A lot of Casio calculators put them on the multiplication and division keys. So you'll want to hit your second or your alternate key, however it's named on your calculator, and then punch those things in. All right, but to get the choose function, NCR, we just scroll over and select that one instead. 10 choose 3, my calculator is happy to tell me, is 120. All right. So that's the mechanics of how to perform these calculations. It's not very exciting. It's just make sure your calculator can do this. If you have a calculator that you are not quite sure how to approach, feel free to drop me an email. I have a pretty extensive collection of calculators. I know how a lot of them work. And when I don't, I can often find things on Google or just a search. So if you're having trouble, you can't find things on your own, get in touch with me and I can try to help you figure out how your particular calculator behaves and where these functions are hiding. All right. Let's take a look at a couple of practical examples. The 150 students in the freshman class must elect a president, a vice president, a secretary, and a treasurer. Well, in order to elect these offices, we need to select from the 150 students 4 of them to be of interest. And each person we elect gets a different title. Everyone we elect gets a different title. The order that we elect these 4 people out of the class makes a difference. And because the order in which we elect these people out of the class makes a difference, we're going to want to use the pick function. So we will take 150, we will pick 4, and we will get a ridiculously large number. $486,246,600. Right. Compare this to a related problem. the 150 students in the freshman class instead must elect a 5-member student council. And in this situation, the members of the student council don't have specific titles. They all get the same title of student counselor. And now it no longer matters which order we select these people in. It just matters which 5 people we select. That's where the choose function comes in. Grab my calculator one more time. That's me. That's the one that's my calculator. And we can punch in 150, choose 5, and my calculator is happy to tell me that this comes out 5,916,00030. Go back, put some commas in. 591,600,030. All right. So that's the basic idea. We have a large collection. We take a smaller group out of it. We think about whether the order in which we take things out makes a difference in the final result. We choose either the pick function or the choose function, and we let our calculator do the rest of the work. I've got one last example, because the phrasing that we usually use here of order matters, order doesn't matter, can be misleading at times. In one lottery game, 7 numbers are drawn from a pot containing the numbers 1 through 28 without replacement. I've talked a little bit about lottery games in the past, drawing numbers from a pot. But if you've ever watched the state lottery drawing, you know what we're talking about. You have the big machine with all the ping pong balls with different numbers bouncing around. Somebody opens up a valve and one of the ping pong balls shoots through the valve, and you read that one number. This is a relatively large pot, and we shoot one ping pong ball out, and then a second, third, fourth, fifth, sixth, and seventh. So we have 7 ping pong balls removed and the rest still in the pot. The numbers are then reported in counting order. And because the numbers are reported in counting order, that means that the order that we draw the numbers in doesn't matter, right? If we draw the numbers 21, 3, 5, 7, 16, 18, and 2. These numbers are going to then be reported in counting order. 2, 3, 5, 7, 16, 18, 21. That's the same lottery result. It doesn't matter what order we draw the numbers in, because whatever order we draw them in, we are going to shuffle them around before we report them. And so that means I want to use the choose function. That is the place that I find students get the most mixed up with the rules for counting. You have to differentiate the action in which you choose things versus the action in which you report things. When I am choosing numbers out of the pot, I'm going to choose them at random. When I report the numbers, I'm going to take what I have and shuffle it around so that they are presented in the counting order, large or smallest to largest. Because of that, no matter what order I pick them in, the result is the same. And because no matter what order I take the numbers in, the result is the same. That's what I mean when I say the order doesn't matter. That's the case that uses the choose function. Grab my calculator one last time. We can punch in 28, choose 7. My calculator is very happy to tell me that this particular lottery game has 1,184,040 different possible outcomes. All right. That's all I have on this topic. A couple of different tools that we're looking at. When it comes to solving problems involving counting, the first step is always going to be look at what you have and make sure that you're approaching it in the right direction. Are you looking at 2 or more steps in your experiment that are independent, or are they dependent on each other? Do they change depending on what's going to happen? When they're independent, you can use the counting principle, multiply together the number of possibilities on each step. When they depend on each other, you have to think more carefully. There's a lot more we could do for a lot of other kinds of complicated situations, which are a little bit beyond what I want to get into right now. Some of it will come up later, most of it not in this course. But however you can figure it out, make sure that you understand what the situation is looking at. Think about which of the tools we have best models that situation. And then from there, the computations are relatively straightforward. Take the results, put them into the calculator. It does all the work for you. Great. That's all I have on this one. Thanks as always for joining me. I'll see you next time.